for an in-class question. I mean, at best, I can try to think of a question sort of conceptually related to this that would somehow probe whether or not I think you'd studied it and understood something about it. And I guess I'll just put a K up here and say K equals to 1, 2, n. Yeah. I mean, example 5.42 is test-worthy. That's the Euclidean case. Yeah. But even the Poincare metric, which is a relatively benign thing, look at the system of differential equations you got to solve on page 227 to find the parallel transport. It is it's pretty tough. So, I mean, if I were you, I would have it on my sheet. I would have an outline of what I have to do. But, you know, the heavy lifting of the differential equation solving here makes it really hard for a direct question, admittedly. But that is what it is. I mean, so the V naught, the vector that you're parallel transporting essentially just sets the initial condition for the differential equation, and then the connection coefficients say how the time evolution of V naught has to go for it to be quote unquote parallel transport. Yeah. But of course, the neat thing is if you pick two different vectors like V naught and V naught tilde, and you parallel transport those, then the parallel transported vectors, you know, maintain the same angle as V and V naught tilde did originally. There's all kinds of neat properties of this parallel transport, right? Which are familiar to our usual, you know, physics transport. But oh, your other question was what?
Just super short on exactness and closeness of forms. And I think exact implies closed, right? I think you can, because if the form is exact and you take the exterior derivative, it would give you 0, which is closed.
So, I got this one Jolly Rancher's got two in the double pack. Got lucky. Well, there's a candy bowl, and it's this thing. My throat's a little bit messed up. This helps. And also the Jolly Ranchers, so, you know, win-win. So I was kind of, that one homework problem I had in Mission 6 was really fun, right? Like, what was it? You're given alpha, how'd it go? Oh, let's say alpha is exact, and let's say beta is closed, just for the sake of discussion, you know? Let's suppose that this is a P form. Let's suppose this is a Q form, just for the sake of discussion. And we were supposed to show that the wedge product was exact. So I was kind of nervous when I first started that problem because I was like, oh no. I thought, when I read the problem, I thought it was to show that it was closed. And I was like, well, closed would be, you know, showing it's closed is pretty easy, right? This would be, well, exact means what? Means alpha is equal to d phi for some potential form phi. Right, that's what exact means. It means it's the differential of something else. So by the Leibniz rule, this is d alpha wedge beta plus minus 1 to the what? P, yeah, of alpha wedge d beta. Okay, but d beta is 0 because beta is closed, right? So closed just means that the exterior derivative is 0. Exact means it's the differential of another one form. So here we get d of d phi wedge beta, which of course is 0 because d squared is 0. I thought that was the homework problem I assigned you guys. when I worked it, I was like, oh, oops, this problem's a little bit sneakier. Because you had to have the sort of insight to go, well, I don't know what else to do here. I guess I'll just guess, beta. Oh, wait, not beta. Something else. Let's say, I haven't used upsilon yet. Upsilon. The often neglected upsilon. So I figured I must do something with like phi. It must be like phi wedge beta or something, because it's got to somehow involve the phi, I figured, and what can I do except wedge with beta? And then I worked out what d upsilon was, I didn't call it upsilon in my solution, which is unfortunate. I should have, but
You take the derivative of minus 1 of k times beta wedge.
phi, yeah. See, but then this is d phi was what? Was alpha. So this is alpha wedge beta. Huh. That's whack. Where's my minus 1 factor? All my letters look the same to me today.
I don't know, but it made sense.
I want the upsilon to be the potential form for alpha wedge beta. And so,
I think maybe,
yeah, d beta is 0.
I think you don't have the minus 1 of whatever, because in this case you wrote alpha wedge beta.
Oh, is this because I...
Alpha was beta wedge alpha.
That's funny.
Or rather, it was that alpha was close and beta was exact, and it was alpha wedge beta.
That would matter, though, right? I mean, if you flip it, there does a sign factor matter. I mean,
Right.
I think,
It's a bit trickier.
yeah, this is a better way to ask the question, honestly. I mean, well, it's good the students get the minus 1 to the form factors, form degree thing it's good, but now, when is exact, when is closed? I mean, if there exists a exact form, if there exists a closed form which is not exact, that indicates that there's some kind of non-trivial topology in your space. So the Poincare lemma proved what? It proved that if the space is star-shaped, basically, that if the form is closed, it can be written as an exact form. You can construct a potential form from it, from a specific integration procedure based on the contraction of the space. And we actually worked through that with you guys, or at least I projected it. That construction, for example, produces the formula for like potential energy from a conservative vector field. That's a special case of the proof of the Poincare lemma. But anyway, so I guess I'll see you guys Monday, right? Right. Sorry I didn't do anything interesting today. Will there be Christoffel symbols? I mean, I think it would be good for you to know what the Christoffel symbol was and how it's defined. And
For example, like Riemannian connection is kind of the way you can do Christoffel, or you can use that disgusting, map that's, what's the word?
I think.
All I know is it's like, it's the inverse of the isomorphism, of an isomorphism that is like 1/2 interior derivative of x times.
oh, his super slick
Yeah.
coordinate-free definition of the connection.
That's the only
Yeah.
two ways to do it, really.
Right. So I think if I had to summarize, I would say you should hopefully be able to do problems like in the homework. Yeah. So Travis is explicit. Travis wants calculate connection coefficients. You said, right? You want to calculate the Christoffel symbols problem. Given a metric. Find the formula for the gradient.
It wouldn't be,
On a generic.
it would take a while, it just wouldn't be challenging, it would just waste a bunch of time.
No, not on a specific, it has to be on a general vector field.
Like, for example, the
Drop it in one to it,
That's all it is.
right? Unless it's.
Well, no, you have to calculate, like,
we have to do the inverse of it.
it's like really disgusting. But very entertaining. For
The
3
inverse of
hours.
a-
Is that one of the homework problems, I think, was something like that.
Was that?
But I think the bulk of the test is probably on wedge products. You know, even calculating determinants with wedge products, like we had in Mission 5. You know,
Oh, yeah, there's a winner you can find.
Are you gonna send out a detailed
That's-
analysis of stuff that you want to know?
I don't think I have such a thing.
Or right for science.
But I would just look back through the homework and, you know, try to make sure your sheet's got everything you think you need on it. And don't stress too much. Okay. Yeah. Go check some of those mechatronic list things off your checklist. Yes? Those can't be checked?
Oh, there's so many things.
Here, I know good question. Like, you could give us the Christoffel symbols of
Yes.
and then do stuff.
Yeah, that's what I was thinking.
And then you can ask questions.
Mm-hmm.
Yeah.
Or force us to memorize the point for an answer.